Hello folks, StylePoint here, and today we're going to be implementing the SERF activation function. We're going to be implementing it in Python using PyTorch. Now, SERF is not necessarily a very popular activation function, but it's also a relatively recent activation function, at least compared to some other activation functions that we have already implemented in the series, such as sigmoid, ReLU, swish, GELU, and so forth. And I thought it would be a good addition to the series because, again, it's relatively recent, but in addition to that, PyTorch does not support this activation function out of the box. Now, with other activation functions, PyTorch actually does support those out of the box. Others meaning the ones that we have already implemented, right? There are built-in implementations that exist in PyTorch. For SERF, there is no such implementation, right? And even though we have implemented all of those other activation functions from scratch, that was primarily for purposes of understanding how it works, as well as for maybe like recreational programming purposes. But of course, those implementations could also be used in production if we wanted to. Now, in this case, in case of SERF, we really need to implement it because otherwise we won't be able to use it. Because again, PyTorch does not provide this activation function. There is no nn.serf, so torch.nn.serf. There is no torch.serf. Okay, so we need to implement this. Now, the first time I kind of encountered this activation function, the first time I saw it was in this Reddit post by user Shronin. SERF activation function, improving swish. And they said, paper looks very promising. What do you think? Anyone tried SERF yet? And they put this link to the paper. So let's click this link. And let's click PDF so we get the PDF of the paper. And there it is, SERF. Towards better training of deep neural networks using log-Softplus error activation function. Okay, so here is S, here are E and R, and here is F, so SERF. And the authors are Sayan Nag and Mayuk Bhattacharya. I hope I didn't mess up the names, and I apologize if I did. But here is the activation function. So SERF is defined as f of x equals x times erf, or the error function, of the natural log of 1 plus e to the power of x. Okay, and then authors talk about some of its properties like upper unboundedness, lower boundedness, differentiability, and so forth. And authors were kind enough to provide the derivative or the gradient of the SERF as well, right? I mean, it's a paper, they had to do it, but that's kind of cool. Now, we would be able to compute the derivative anyway, right? Because we just know how to compute it, right? It's just a product rule and then like the sum rule in this case of finding the derivative. And we know derivative of x, we know derivative of erf, we know derivative of the natural log, we know derivative of e to the power of x. And derivative of 1 is, it's 0. And so we would be able to compute it anyway. And even if we didn't know how to compute it, right? Torch has a built-in autograd engine, then that would compute it for us, right? So, but it's super cool that they provide it. And we're going to use this actually in a video in our implementation, right? So, they also compare this to some other activation functions here. Swish, mish, and SERF. So this is swish right here, the green plot. And then we have the this dark blue plot for the SERF, right? And they seem very similar, right? And authors point this out right here as well. So SERF is closely related to swish, which can be noticed in its first derivative. Okay, so we see it here. The first derivative of SERF is given as this, and we see this term here, x times sigmoid of x. Well, that's just swish, right? And they substitute that term or that expression with the swish here. So yeah, SERF and swish, they're kind of similar. Now, I have also generated the plot using matplotlib here, and here is SERF. And here is swish, okay? So to check this for ourselves as well, here it is. SERF, swish, very similar, right? Now, SERF has like a deeper dip here, right? And then it comes back up. Swish does not have this, well, it still has this dip here, but it's not as deep as in the SERF activation function, okay? They're very similar, okay? Now, SERF is also similar to ReLU in a way, of course. ReLU is more like it's linear, right? It's two lines joined at point 0. They're merged here. In case of SERF, of course, it's a smoother variant, right? It's a lot smoother than the ReLU. Same could be said about Swish, right? So Swish and SERF, they're very similar, but SERF and ReLU are also similar. Now, some of the advantages, of course, of SERF over ReLU, that would be, well, it would depend on the problem, but one advantage that we can see here is that it's more expressive in a way, right? Now, ReLU, for positive activations, it's going to map positive inputs to positive outputs, so that's cool. That allows for a better kind of expressiveness. That allows a neuron to express a strong opinion. And the same could be said about SERF, right? For positive inputs, we're going to get positive outputs, or unique positive inputs are going to be mapped to unique positive outputs. But in addition to that, even for some of the negative inputs, we're going to have negative activation values. And that can be cool. That can be advantageous, at least over ReLU here, because not everything is zeroed out. We're not suppressing all of the negative inputs. And this is similar to Swish in a way, right? Even in Swish, we have this little dip here, and that allows for mapping some negative inputs to negative outputs. So they're not going to be suppressed or zeroed out. Okay. Other than that, of course, SERF introduces nonlinearity. That's super cool. That allows us to approximate nonlinear functions. If all we did was use linear functions, we would only be able to approximate linear functions, right? So that's super cool. And well, if we consider like the performance of SERF, of course, SERF would be slower than ReLU because, I mean, the way we can implement, one way to implement ReLU at least is using ternary if operation, and it's just literally one comparison. It's like an if statement that has broadcasting built in, right? Torch.where is what we can use. Now, in case of SERF, we need a bit more than that. We need ERF, the error function. We need the natural log. We need to add. We need to exponentiate. We need to then multiply. So it's a bit more complicated than that. So it's going to be a bit slower because we just have more computations, right? There's more to do. Okay, so that's going to be a bit slower. But in practice, if we run this on the GPU, we're going to see that there's actually not like a huge performance penalty for using SERF over ReLU. And they're like roughly similar in terms of performance if we run this on the on a good machine with a good GPU. Okay, so there's no the performance. There's not a huge performance difference. Okay, and SERF versus Swish, these two. I would assume the performance difference here would be even smaller. Okay, so I have not actually have not written the code for benchmarking these, but just looking at the expressions here, they would be kind of similar. But yeah, I mean, SERF would probably be the most computationally intensive activation function. Okay, so now what we're going to do is that we're going to implement this. We know how to compute both the SERF as well as how to compute its gradient, right? So we're going to go ahead and do it. Now, the way we can do it is just, we're just going to follow the paper, and let's move this paper here, okay? And let's just look at what we have, right? I have the boilerplate for the SERF activation function prepared here, so we don't have to write this. It's just the class definition pretty much, and we define the API for it, like the forward and backward. Okay, so for the forward method, we do f of x equals x times ERF of the natural log of 1 plus e to the power of x. So let's do this. So we return data times torch.erf of torch.log, that's natural log, of 1 plus data exp. And that should be it. Okay, that's the forward method. Now, for the back propagation, to compute the gradient, basically, right? So we do need the result of after applying SERF. So we need the SERFed values, right? So we need the values we get after applying SERF, but we also need the tensor, the original tensor. So maybe we can do it this way. We call this result, and context save for backward. We're going to save both the data and the result, and then we're going to return a result. Okay. Now we have both data and results stored here. Okay, then we can go ahead and reuse them here. We can unpack them from saved tensors. And we can follow the formula here now. So they call this expression P, and we're going to call it the same, kind of give it the same name. So this is going to be 2 over torch.pi to the power of 0.5, so squared from the pi, square root of pi, and then that is multiplied by this expression, e to the power of negative log. Okay, so negative natural log. So the way we can do that is maybe we can do something like this. So 1 plus data x. So we initially compute this. That has to be, we need to find natural log of that, okay? And then we need to find the square of that. We need to square it, and then we need to exponentiate it. Okay, I think that should be it. That's the p. Now, we need swish, and actually PyTorch has swish built in, and we can reuse that. I mean, we could have implemented swish on our own. It's just data times torch.sigmoid of data. But we can just reuse whatever PyTorch provides. It's called not RelU, but the SILU. Okay, PyTorch calls swish SILU, so we can use that. Then we compute the gradient. So it's p times swish of data. Now notice that we're initializing SILU here, so it's like a function pretty much. So we then need to pass data to it, and then we add actually result over data, and finally we perform the chain rule, right? So that's the core of backpropagation, right? So that's the chain rule. Multiply the gradient we got up until this point by the gradient we got by the gradient of SERF, by the gradient we got here. And that's going to be the entire implementation of SERF. Now for testing, we have the simple test here. Of course, in production, we would have to have more tests, right? So, but for this video, I think this is going to suffice. It's a simple test. So for testing, we're going to do autograd.gradcheck. So torch autograd.gradcheck, that does gradcheck. It's a utility function provided by Torch. And what gradcheck does is that it compares our gradient approximations to the numerical approximations. And if they're close enough, we're going to say that the gradcheck was successful. And otherwise, if they're not close enough, we're going to say that it was unsuccessful. But let's see what we get here. There it is, gradcheck successful. So super cool. Okay, so it means our implementation is good. I mean, of course, once again, we would have to have more test cases to truly verify that it is a correct implementation. But now I also want to show you the alternative implementation using the PyTorch's autograd engine that it has built in. So this alternative implementation relies on PyTorch to compute gradients for us. So all we're going to do is that we're just going to copy this, right? And we're going to just say that, just return data times torch.erf of torch.log of 1 plus data x. So just perform the forward method. There is no context passed to the forward method. There's no backward method at all. We're not saving tensors for backward. We're not unpacking them. We're not implementing the backpropagation manually. We're not doing anything other than implementing the forward method. And of course, we can do that because all we're using here are the built-in operations, right? So we're using operations for which PyTorch knows how to compute gradients, like multiplication, ERF, natural logarithm, exponentiation, addition. So these are the operations that are provided by PyTorch, and PyTorch knows how to automatically differentiate or automatically compute derivatives for those. And now this implementation would be pretty much the same, except for instead of doing serf.apply, so the API is going to change. With torch.autograd.function, if we inherit from it, we need to do this serf.apply. And apply is like apply function pretty much. But in case of nn.module, right, we inherit from nn.module and then we perform inheritance here. We do need to do that in this implementation. In that case, we just initialize like a class, serf, and then we can test this. And there it is, gradcheck successful. Super cool. Okay, so this is the alternative implementation. Now, if you were to ask me which implementation I would use in production, I would probably use this implementation. The reason for that is not because PyTorch has like a bad autograd engine. It has a very powerful autograd engine, and I would encourage using it when you can. But in this case, it's just the backward method is useful because it's almost like a documentation. Okay. I mean, maybe we're going to use this implementation, but then we'd have to document how to compute like the gradient, because I think it's very important to know how to compute gradients for all of the functions that we support, right? So it's not only useful, but I think it's necessary pretty much to know that. Of course, relying on the PyTorch magic, right? This AutoGrad engine, it works, but this is just, I think, what is fundamentally a better approach, because we know how it works, we understand it, and we implement everything on our own. So this is going to be it for this video. I hope you found it informative. I hope you found it helpful. And if you have any questions or suggestions, please feel free to comment in the comment section. And I'm going to see you next time.